Cal EPA for providing the space. And I'm going to talk, as it says, about predictions in California. And part of this is a follow-up to what Phil Duffy talked about last time. He talked quite a bit about predictions for California and what they might mean. And I'm actually going to digress quite a bit and go back and look at the models and how these predictions are made to give you a little better feeling for what really happens. People say it's going to be 5 degrees warmer. What does that really mean? The slide here just, these are the covers to the 3 IPCC reports. Oh, I have a pointer. And these are the basis for most of what I'm going to talk about and most of what people would talk about in climate change today. These are the recent reports just last year. What I'm going to do, as I say, is talk about how are the projections made. IPCC is the Intergovernmental Panel on Climate Change. What are the global climate models, which are the basis of much of the projection that we're talking about? How are these actually evaluated? Why do we think they're approximately correct? What do they say about California? And what might be the practical implications? So we're going to go on sort of focusing down towards California. Now, the modeling is a fairly complicated set of modeling procedures in which this, what I'm calling the IPCC modeling strategy. There is first, and I'm going to do this a little more detail in a minute, but there's first some sort of social economic model to estimate the emissions so that we know how much greenhouse gas we put in the atmosphere right now. The question is, how much will we put in 50 years or 100 years from now? These are based upon some social economic estimates. We'll get to that. After those are estimates of emission. How much mass per time is put into the atmosphere? The next thing to do is one has to use some sort of carbon budget or some sort of budget model to say how much of that gas remains in the atmosphere. What is the actual amount of greenhouse gas in the atmosphere or other things? This modeling procedure also, we're going to add in, or they add in, so-called some things we know the natural variability. There are some things other than human activity, which is influencing climate. One of them that we know, and which we can predict into the future reasonably accurately, is sunspot cycle. We know that there's a small variation in the solar cycle, the solar output that occurs around the sunspot cycle. We can predict that in the future. There's another thing that's a natural effect on climate which we can't predict, and that's volcanoes. So that's not included. Then we take all of these things, or basically the gas concentrations and the variability of the sun, and we put it into a global climate system model. And that's what I'm going to do quite a bit of detail on. And then we run that model into the future, and then we look at, whatever year you want. So let's go on. Talk first about the social economic model. Well, these are not models in some sense. What is used are scenarios. These are best guesses of the sort of probable range of emissions. And this describes basically the sort of set of ranges. A side are where we have relatively large population growth, relatively large economic growth, relatively large use of fossil fuels. The B side is where there is less use of fossil fuels and other things. The 1-2 side here, which is up-down in this case, is there is some sort of global controls or global treaties, etc., which somehow control or manage greenhouse gas emissions or other emissions. And the other where there's more localized control or really no control. The sort of most extreme greenhouse gas emissions are going to be down in here in the A2 category. That's basically where there's a lot of growth, a lot of use of fossil fuels, and no regulation. And the sort of the most controlled would be up here, where there's a lot of global regulation and very environmentally oriented control. So this is sort of the range. We'll see a little bit what this means. Just an example of how this is done. One of the obvious things is population. Population is an important driver for climate simply because the more people there are, the more fossil fuels get used in general, and the emissions there are. And so we're here, 2000 roughly. So these are the possible population changes which are suggested in these scenarios. Or in a group of this is A and B, ones which are used. You can see there's a pretty big range. It's a factor of 2, practically. Because we don't know in 100 years what the population will be. So this just sort of brackets what we think the likely population will be. This here just shows sort of the other economic, social part, where there's a high dependence upon coal, a relatively high dependence upon gas and oil, and a relatively high dependence upon renewable and nuclear. And so in here, this determines when you're down in here someplace, then you have less fossil fuel use per person. So this is a way to scale the people. And when you're up here, you have a relatively large of oil and gas fossil fuel use. And here you have a relatively large amount of coal. And it makes a difference because there's more carbon dioxide with the coal than there is for the same amount of energy, for instance. Now, once you have these emissions, so how much gas or what a material is emitted per year or per time period, then you still have to know how much actually is in the atmosphere at a given time period. And so this is to represent the sort of the estimate of the emission, which goes into some model which determines how much remains in the atmosphere. What's the concentration in the atmosphere? Why is this important? Well, we know that about half of the carbon dioxide that we put in the atmosphere right now goes out of the atmosphere very quickly. Goes into the oceans, goes into soil, goes into vegetation. And, it's a first approximation, that's what we expect in the future. But there are attempts to make better estimates of what fraction of the material that we emit actually stays in the atmosphere. And this is different for different materials. Carbon dioxide is different than methane or one of the other greenhouse gases. They have different lifetimes. And this just says that some of it can go into plants, a lot of it can go into the oceans, so forth. And some of it is isolated. There's a large amount of carbon deep in the ocean, at the bottom of the ocean, which can't alter, at least over our lifetimes, over many lifetimes. So anyway, these models are basically used to determine how much carbon dioxide and other greenhouse gases, including aerosols, is in the atmosphere at a given time in the future. This is an example of this. So here we have, here on the left, we have these various scenarios. So A, and B, etc. So we see, for instance, if we pick this green as A2, one of the most extreme, this is a very large growth of carbon dioxide. So this is emission. So this is increase in the amount of carbon dioxide per year put into the atmosphere. We can see other ones here. We have a fairly large increase, and then we have some sort of international regulation around 2050 where it dictates a decrease. Here we have a much smaller increase and still a larger decrease. So these are the kind of social decisions that we, I guess, don't know for the future. But again, the attempt is to bracket the largest amount of emission and the smallest amount of emission that is likely under some reasonable case. Now, so this is the emissions. This turns out to be the actual carbon dioxide concentration from each one of these lines. So there's a corresponding line here. We see that they tend to be more regular because the more you put in the atmosphere, the more that's actually absorbed by the ocean and so forth. There is a correspondence to sort of negate to some extent. But in any case, it's still a relatively broad range of carbon dioxide in the atmosphere. In this case, we have here the smallest amount. We have roughly 1.5 times what we have today. We're down right there today. And then in other cases, we're double or more than double what we have today. So that's, again, the range of carbon dioxide in one of the interesting things is to look at this green line, this B1. This is the one which has a large global environmental controls. You see that after 2050, the carbon dioxide emissions actually decrease. But we see here that the actual amount of carbon dioxide in the atmosphere increases. How is that? Well, these are, of course, there's still emission. Bottom line here isn't 0. The bottom line is 5 in these big, very big. So we're still adding carbon dioxide, just a lot more slowly than we might in these other cases, or even than we're doing now. But we're still adding it, and so the amount of carbon dioxide is still going up. Probably very slowly compared to here, but still going up. This right slide shows the other side of this, in that there are other gases. Besides carbon dioxide, we have other greenhouse gases like methane and nitrous oxide, etc. And the other thing that's important for climate, or one of the other things, sulfur dioxide, because they become particles in the atmosphere, which reflect sunlight and tend to cool the Earth rather than warm the Earth. We need to know about those as well. These are actually CO2 emissions, SO2 emissions. We see there's actually a pretty broad range here. Future. This is actually related to burning of fuel, so these two things are tied. Much of the sulfur dioxide is from burning coal, so there is a link between these two curves in some sense. But we also see in general there's a decrease assumed in all but one of these, and this is actually an early not used in this. The decrease is because sulfur dioxide is a fairly standard air pollutant. And almost certainly we will regulate it because the air in Beijing or in places where it's growing very fast will get so bad that they'll put a strong regulation on it, but independent of global warming, independent of global climate change. And the regulation kicks in at different times in these different scenarios, but there's still regulation which tends to make the emissions go down. So again, these are just our best. So again, if we look at 2050 or 2100, these are sort of the range of the different values of these things which we feel are likely. As I said, in addition to forcing these models with the greenhouse gases which have a control over the radiation budget of the atmosphere, we also can predict into the future, for instance, small changes in sunlight. This is just an example of how this dotted curve is the Sunspot Cycle. And this is a very regular 11-year cycle, which is known for back several hundred years. Actually, Galileo saw the first sunspots. Takes a weak telescope, and they've been keeping track of it since. And it's a very regular cycle. This is a short segment, just a few year segment of the measurements from a satellite and the amount of sunlight at the top of the atmosphere. And it's now known there's a good link between these two. The point is you can project this change in sunlight into the future by just projecting the sunspot cycle into the future. So it's a fairly easy statistical projection. That's the one natural change occurring from the outside that affects climate, which are put in all of these models. Now the models themselves are complicated. This I pulled off the web. This is some sort of Rube Goldberg machine. But this is the way some people think about these, instead of garbage in, garbage out. But of course they're not. And I want to talk in some detail about what they are. This is a schematic which sort of describes the physical processes in a modern climate model. And in this case, we have a lot of things going on. The guts of the model tend to be the weather forecast model, which is here related to what's called the atmospheric circulation. This is the winds, the temperatures, the precipitation, etc., that occur in day-to-day weather and occur in climate. And that's a major part of all of these models. In addition, there's things which relate the sunlight coming into the atmosphere and heat leaving the atmosphere, and which are the main controlling points for the weather and the climate. So this is, we can get back as a brief review, is what the greenhouse effect is all about. Greenhouse effect is related to the fact that certain gases in the atmosphere absorb heat that goes up out of the atmosphere to space. If those gases weren't there, the gases are primarily carbon dioxide and water vapor, two other gases. If they weren't there, heat that starts out of the ground would basically go straight to space and be lost. Just go out to space forever. But with these gases, the heat starts out, but some of the time at least, it's absorbed by those gases, one of those gas molecules. But it doesn't stay absorbed very long. It's re-emitted out. It's absorbed and emitted in a matter of microseconds, very short time. But when it's re-emitted, it's not necessarily re-emitted back up. It's re-emitted in all directions, but up or down is, in our case, is the important thing. And so part of the radiation that was going out to space and going to be lost, it comes back down to the surface, warming the surface, adding energy to the surface. The natural greenhouse effect increases the surface temperature about 18 degrees C. What's that? 30 degrees Fahrenheit. So the Earth would be both basically unlivable if it weren't for the natural greenhouse effect. The greenhouse effect that people talk about are related to the fact that carbon dioxide and other gases add to this. Mean that it's slightly more likely that energy coming up that might go to space is absorbed and then sent back down to the surface. And so every time that happens, you tend to warm the surface relative to what it would be. So increasing greenhouse gases, carbon dioxide, methane, nitrous oxide, and CFCs, which are the chlorofluorocarbons that are used in air conditioning, et cetera, are the major anthropogenic, human-related greenhouse gases, and go to heating the Earth. The other thing that affects the climate is the sun. And we talked about the sun output changes slightly, but also volcanic aerosols put in dust particles in the atmosphere which reflect sunlight back out to space. Or if it's reflected back to space before it hits the ground, then that tends to mean there's a cooling of the Earth. Because the sun is just like having a big mirror at the top of the sky, and part of the sun never reaches us. So we tend to cool. So changes in the aerosols or natural changes in the clouds can affect the amount of sunlight as well. So these climate models take into account these radiation factors, take into account the weather factors, and then also take into account other things. For instance, the ocean circulation. The ocean is important because it takes heat from the equatorial regions and moves it towards the poles and around. And that affects the climate. We have to have a model for interactions with the land. Changes in the land affect the climate. If you make the surface whiter, in other words, you replace a black soil with concrete, then you reflect more sunlight to space, or vice versa. If you replace a sandy soil with asphalt, you reflect less sunlight to space, have more energy being applied. All of those things affect the climate. The other thing is, for instance, ice. Ice is an important regulator of climate in that if, let's say, the Earth cools slightly, then you add more ice to the polar regions, and the ice reflects sunlight to space. If the Earth warms and you melt ice, then less of the sunlight that would have been reflected to space is reflected, and more energy is absorbed. So the Earth warms even more. So ice is an important control or mechanism for climate. So I'm going to talk a little bit about each one of these separately. So the atmosphere. Most of you, or many of you may know that atmospheric models tend to be these things in where you divide up the Earth's surface or the Earth's atmosphere into chunks. So this is an example. This happens to come from the British Met Office. This is an example where we have Great Britain, and we have a bunch of grids, grid space. So we divide the Earth into grids, and then we divide the atmosphere into columns, which we have layers here. We have a little cube. Each one of those cubes in these models, we calculate or we solve an equation, or we solve a number of equations. We solve equations for conservation of momentum, which basically determines the winds. Solve equation for conservation of energy, which determines the temperature. Solve equation for conservation of mass, which is partly related to determining the pressure. We solve the equation for conservation of moisture, which determines the amount of water in the atmosphere. We solve equations for conservation of ozone, for instance, or some other things as well. So we have a bunch of fundamental equations which are solved for each of these points around the globe and in the vertical. Those are what are called and also we solve the equations for the interaction between the points. So if it's warmer here than here, we'd expect heat to go between the two. Or if warmer here than here, we'd expect heat to go between the two. So we solve those kinds of interactions as well. Those are all what are called the large-scale interactions. Those are using the fundamental physics. But there are other things which are important which we don't know so well on that scale, meaning on the scale of these grid spacing. Some of those things are obvious, like clouds. Clouds are relatively small. Clouds are in the order of a few meters, hundreds of meters, a few kilometers in size and diameter. Those are much smaller than the size of these boxes. We're going to talk about the size of them. So we have to, but they're important because clouds reflect sunlight. Clouds absorb heat. So we have to understand the sort of cumulative effect of the clouds which are in this box on the climate. So those are what are called subgrid scale processes, which we parameterize in some way. And these are very highly sophisticated things, which are largely come out of weather forecasting. So the same kinds of problems which are in these climate models are in the weather forecast. And actually, the atmospheric models, part of the climate models, are basically weather forecast models. And they've been derived from the current. There are other subgrid scale things I'm going to talk about later, but that's the cloud that's the most important one. This gives you an idea of the resolution, so-called. This is the size of these boxes. These acronyms, FAR, SAR, TAR, and AR4, are these IPCC reports over the last 18 years. So this first assessment report, second assessment, third, and fourth assessment report. As time has gone on in the 18 years, the computers have become faster, and the ability to do with smaller and smaller spacing has become easier and easier. So first, we started with the climate models. These boxes were 500 kilometers across. That's the width of the state of California. So they were very crude. As we went to the present, they're about 100 kilometers across. So we've divided now the state into 4 or 5 boxes across and many boxes south. So we can at least see California in these. This is an average for, there are many different models, and they all have slightly different. So this, and again, we see Europe today. We can see now, for instance, here, England was missing from the world because it's too small to include easily in one of these boxes. So we can now see that England is there, and so forth. So it is a roughly realistic system that we're looking at. This is still somewhat cruder than a typical weather forecast, but still, it's comparable to the weather forecast. The other thing that's changed over time is the sort of physics that's available that's included in these models. And it's really the sort of subgrid scale things primarily that are, although other things as well. In the first assessment, it was basically a weather forecast model with what we call a swamp ocean, which means there's water, but it doesn't do anything. It just sits there. It doesn't move, doesn't changes temperature, but only in a local sense. The next important improvement, or the major important, was to add a so-called dynamical ocean. I'm going to briefly talk about it in a second. Basically, it's a model of the ocean currents and the ocean temperatures, et cetera, which occur in the same way as we do with the atmosphere. Then improvements were added things like aerosols and dust particles and more complicated things in the atmosphere. Then most recent ones from the AR4, we have things like interactive vegetation. I'm going to talk about that in a second. In better ice models, ice is in the picture. And some models have chemistry, although that's not so common. So there's an evolution to be more complete and include in a better way the things we think are important. And also in a better way as well, because this had clouds, but the clouds here, the sophistication of the parameterization for clouds is much better in the current models and more realistic. And again, these are forced or proven by what happens in weather forecast models. They do a much better job than in the past. What you get out of these atmospheric models is you get weather. These models are forecast ahead in time steps. So you leap ahead in time using numerical methods, and typically anywhere from 10 minutes to half an hour. So when we talk about climate in 2100, we've gotten there by calculating the weather between now and 2100 in half-hour time steps. And when we talk about what the weather is in that time, we're actually not talking about the weather. We average, let's say, over a 5 or 10 year period to give you a sort of typical situation, because it's varying all the time. In 2100, it's in the same way as it does today. And so what you get at any given snapshot is something like this. This is actually a weather channel. This is a forecast model output. But you get something like a forecast model output, something like regular weather all the way for 100 years. So that's why there's a lot of computer time. Not surprising. Now, I was saying something about the oceans. The oceans are also important. The oceans, heat comes into the atmosphere from the sun, and we know most of it gathers around the equator. The equator is warmer than the poles, and it has to go poleward, or at least it, sort of think it naturally migrates poleward. And a third to a half of that poleward transport is actually in the oceans. The oceans are an important part of the climate system. And the oceans are another model, another computer model, which is very much like the atmospheric model in the sense that you divide the oceans up into grids and columns now into the ocean. And you have conservation of momentum, salt, and heat, etc., for every point on that, in that grid, or every cube. You go forward in time. Well, the important part is that the top of this is actually the atmosphere, because much of the ocean circulation is driven by the winds of the atmosphere. So there's an interaction between the ocean model and the atmospheric model in that the ocean model is being forced by the winds of the atmosphere. Because the atmospheric winds, of course, blow across the ocean, and they drag the ocean slowly with them. Much more slowly than the winds blow, but that's the primary thing that drives the ocean currents and does the things like change temperature, etc. And out of these ocean models, you get weather as well. You get every half hour, every hour, you get what the ocean looks like. Its temperature, its currents, this represents, little arrows represents the currents, etc. Where is this? Any spot where this is? That's your geography. Japan, right. This is the so-called Kuroshio current, a strong current like the Gulf Stream. So this just represents what the output of one of these models would look like in some time period, now or in the future. Another set of models which are important are related to ice. I said ice is important because ice is reflective. So if you melt ice, you have more energy not being reflected to space and being absorbed by the ocean surface or the land surface, and that tends to heat the Earth. So you have to have a model of ice. And there's models of ice over the ocean, floating ice like in the Arctic Ocean. So there, ice forms because the water cools down below the freezing level of ocean water, and you get ice forming. Over land, ice is a little bit different because it's mainly snow accumulation than becoming thicker and denser. But you also lose ice in some way. You lose ice over the ocean because the ocean underneath warms or because there's warming from above. You can have both processes. You lose ice over the land mainly because of surface, although other things happen. And the land ice is actually fairly complicated because big glaciers, they move slightly. That's icebergs. Icebergs is because the big glaciers are moving very slowly from the tops of the glaciers down to the ocean, and they're naturally dropping off icebergs. There's a very slow, what's called plastic flow, which is like soil-type flow or something like that, where you have a very slow, very resistant kind of movement, but there's still a movement. And of course, that speeds up, and you have more icebergs, and you have a loss of the ice on top, or at least you could. There's also, so it's a complicated matter. But all those models now have some sort of estimate of how the land ice and how the sea ice is changing. And as I said, they also have an estimate of how what the interaction is between the atmosphere and the ground. And the ground, especially including vegetation, because vegetation is important in terms of altering evaporation and so forth. And so there are a number of things which have to be included in order to have a realistic ground surface and therefore temperature at the ground. Because the ultimate thing we're looking at, whoop, there goes my water. The ultimate thing we're looking for is how the air temperature very near the ground changes. And it's this ground temperature which is the primary determinant of that air temperature. So changes in the vegetation, for instance, can affect that. Changes how the vegetation interacts with the atmosphere can affect that. So finally, you have to put all of these things together. And this is a sort of an aside, but back, numerical weather prediction, these computer models were actually envisioned first by a person called Richardson during actually World War I. He was a conscientious objector, was an ambulance driver. He had a lot of time on his hands. And he worked out in big notebooks how to predict weather into the future numerically, which nobody had ever done before. Wrote out the basic equation. And back here in the 20s, he wrote a book on this, which became a very important book. Turns out he failed. He actually tried this in the 20s, and the forecast failed for reasons we know. But at that time, he envisioned to be able to make global forecasts, we'd need 64,000 mathematicians working day and night, doing arithmetic to do these calculations into the future. So he envisioned this big Colosseum-like place. These are banks of people. And they all sort of report up to the high monkey mucks up at the top here. And they put all of these things together. And that's your forecast person. But of course, now we don't do that. We have computers. And we have, the largest computers. This is just NCAR. Some of you know the National Center for Research. Okay, so now people make these forecasts. And one of the things that's important is the question of how much can you believe these forecasts? Well, one way to test how much you can believe these forecasts is to basically make what are called hindcasts. Predict the last 100 years based only on the carbon dioxide and the sun and the other things which we know control climate, but change nothing else. So in these cases, these models typically start around 1850 with a best guesstimate what the climate looked like then, and then just evolve to 2000 or 2005 when the IPCC thing deadline. You can look over the last 30 years, let's say, of those projections and compare against real observations. Say, how realistic are the model results compared to what we know really happened? That's what's been done in quite a bit of detail. This is just an example of that sort of thing. What is shown in the lines is the temperatures, annual average, I think. The temperatures around the globe, these in Celsius is 24 degrees C here, 24 here, and it gets colder. The important thing is the colors. The colors, unfortunately, they're a little washed out here. The colors are the errors. They're the differences between the temperatures predicted for some time period and those actually observed for that time period. Averaged over a period. We see that by and large, the temperatures are over much of the tropics, much of the southern hemisphere, agree to within roughly 1 degree. So there's really very little error between what the models predict based purely on knowledge of the sun, knowledge of the gases, etc. What is actually observed. Now there are some places where there are differences. These are places in the high latitudes where there's actually quite a bit of variability, and there's a place over here in the Atlantic Ocean which I don't think is very well understood. But even those large areas are typically in the range of 2 or 3 degrees. So by and large, these models do a pretty good job of emulating current climate based upon these very broad general inputs. This is another example for precipitation. It's shown in a different way. Which one is which? The upper model is the observed, and this is the model. So this is the observed precipitation. The scale is here. It's a funny scale. The white is where there's a lot of precipitation. It's centimeters, so this is more than 3 meters of water in a year. And so this is the observed, and this is the model. We can see, by and large, there's a lot of agreement. Precipitation is relatively difficult. Certainly, the agreement is not as good as temperature. But the basic features of the precipitation patterns around the globe are shown in these models. Areas that the models seem to actually have a little not quite enough precipitation in this region, for instance, and over parts of India. But by and large, they show, for instance, the large rainfall regions of Africa or over relatively accurately. Precipitation is relatively difficult, partly because I was talking about subgrid scale processes before. Precipitation is, of course, tied to clouds. Clouds are small, and also the processes that produce precipitation actually involve tiny things. You have droplets falling. Well, these droplets are millimeter size. So actually, in models, they try to keep track of how they grow from very tiny drops at the top of the atmosphere to rain-size drops like centimeter-size drops at the bottom. So there's a lot of physics involved in that as well. And so it's not a perfect science in that sense. Other things, this shows heat transport, ocean heat transport. So this is the amount of energy transported either towards or away from the poles. In this case, positive means going towards the North Pole. Negative here means going towards the South Pole. A couple of those lines are black in the dash. You can't quite see them, are the observed. And these are various models. And there's a fair amount of uncertainty actually in the observed as well. Because it's hard to actually measure how much heat is being transported by the oceans on. But we see that by and large the models show at least the proper envelope, and some of the models do very well, very close to being the upper. They tend to underestimate a little bit what's happening in the southern. This is a similar thing for east-west winds across the oceans, I think. In which, so positive means from the west, negative means from the east. And again, as a function of latitude, north to south. We see that someplace in here is the observations, and then the models. And by and large, the observations are lost within the model, so that the models quite accurately represent what's going on. Again, so this is based upon models which started out 150 years ago, and it's the last 30 years of the weather. Now, there are some problems, and the clouds are one that people have talked about in the past. And so this is the observations of cloudiness for December, January, February. A pretty ugly color scheme, but in percent. So these are really a small amount of cloud in here and relatively. And this is the model calculation. Actually, this is the mean of a number of models which are gone into this IPCC report. They've just been clumped together. And we see here that there are some differences. For instance, here there's a place of not much cloud, and that's not really well shown in other major features are obviously the deserts. There's a Sahara Desert here, and the Sahara Desert here. It looks pretty good. The main rainfall regions here, over the Amazon, and here, and so forth. So there are, qualitatively, it's reasonable, but there are details that people are concerned about. This now is something, a figure similar to what you've seen before. I think both speakers have shown a figure like this. What we have is a couple things here. Let's look down at the beginning up until 2000. This is a projection based upon these models from 1900 to 2000. Well, not all projection. The black line is the observed global average temperature change. And actually, Northern Hemisphere. This is the Northern Hemisphere average temperature change. So, and this is something that's fairly well known. There was a fairly rapid increase in the 20s and 30s, a fairly broad plateau in the 40s and 50s, and then a more rapid increase again in the 70s or from the 80s on. That's the observed change in temperature, which comes out of all observational records. The green line is the average. Oh no, the green line is the average of 18 models. We see here that it shows similar thing. It doesn't show quite so well this rise and plateau. It shows a more gradual rise and then a rapid rise. And the funny yellow color, which is not what it looked like on my computer screen, is from a particular model, the CCSM, which is the one from NCAR, the one from the place. And it shows something like that. It actually has a rapid rise, there's an actual decline, and then the rise in recent time period. But qualitatively, all three of these look very much alike. So this is part of the reason we have confidence, and there are other charts like this in these models, that not only do they give us average weather reasonably well, they show us how the weather has changed over the last 100 years also reasonably well. And again, the only inputs for these models are the greenhouse gases, aerosols from either natural or anthropogenic, meaning volcanoes, and changes in sunlight. Those are the only things which are affecting those numbers, those averages. Obviously, what's going on in the future is these here. And we have, to simplify things, I have just two. One corresponding to A, which is the controlled scenarios. So this is the emission scenarios, and this corresponds to B. So this is where we have a fairly large control over the climate, over global emissions of greenhouse gases and other things. This is one where we have over little control. Up until 2020 or 2030 or so, basically the projected climate change is very small. But not surprising, when we don't have much control, the projected climate change becomes much larger, up to about 6 or 7 degrees centigrade, because these are all in centigrade, compared to about 3 degrees centigrade. So this is the projected climate change over the next 100 years in these two scenarios. We expect that the actual value to be someplace in between. This is more or less brackets what are the reasonable emission scenarios, the reasonable maximum minimum emissions. So this is what we think is the bracket of the temperature change in the next 100 years for the globe. One interesting thing is, well, 3 degrees doesn't sound like that much. Why are we worried? Well, yes, this is the global average number. Some places don't change very much. It turns out in the tropics and the equatorial region, the changes are small, and the polar regions have changed. That may be, I don't know. So, some places will change a lot more than 3 degrees. The other thing is that 3 degrees may not seem too bad, although in Sacramento, if the temperature went up, average temperature went up 5 or 6 degrees in the summertime, I think we'd all feel it. But another way to think about it is, in the last ice age, up to the last ice age, the average global temperature was 3.5 or 4 degrees colder than today. So for something which we know is a big thing, that we know is important in terms of climate change, obviously the opposite direction, 3 or 4 degrees is very important. So it's likely that 3 or 4 degrees, or even in the warm side, will also be very important. There are consequences because we know. So both of these tend to show that, although one is on the very margin of that, and one, of course, the 6 or 7 degree temperature change is very much more extreme. One aspect of this is, or one important part of this is that does mean that regulation can help. But regulation is what's going to determine whether we're up here or down here. It may not get us much below there, partly because we're not going to stop using fossil fuels. Fossil fuel greenhouse gases, which are in the atmosphere, stay for a long time. So the effects of what we put in 50 years ago are still with us. But nevertheless, we can have a really broad range in what are the real outcome of the greenhouse gases. Okay, now we're going to look at California. Now, what these are looking into the past. So this is looking over model calculations for the last 100 or so years, and looking at the last 30 years, at the climate change in the last 30 years versus observation. So obviously on the left we have the climate change to be observed, and this is a scale, so a half degree to a couple degrees here, increase almost everywhere. So we have here, except for that point there, every place in western US, you can't quite see it as California, every place in the western US is warm in the last 30 years. And it turns out in this case, the largest is up here in southern Canada. This is the mean predicted from these calculations that started in 1850 to the present change for that 30-year period using the same reference point. We see that we have, again, the same general pattern, actually a smaller change over the ocean than observed, a little bit smaller compared to the coast. But the same general pattern, the warmest up here in Canada are actually north, but the same general pattern. This also shows us these boxes are boxes of the sort of crudest climate model that we use. I've gridded sort of the lowest resolution. This happens to be the result for this one particular model, the CCSM. You can see it agrees with the observation, with the mean quite well, and actually with the observation. So we have a lot of confidence in the temperature predictions made by these models, almost all of these models, including this one I'm going to go with. Now, if we look at precipitation, things are not so good. So this is the same sort of thing for the observed. These boxes represent the change in precipitation over a 30-year period, in the most recent 30 years relative to some reference. In this case, the green means increase. Here's the scale over here. This is from the 18 model mean. This is from the CCSM. Well, you notice there's a little bit of agreement here with the 18 model mean. But there's basically, the models show relatively little change compared to the observations. So actually, observations show a slight increase. Turns out that even the observations, several different sets of observations, have a fair amount of disagreement between themselves. Precipitation is a very difficult variable to measure because it comes so sporadically. It's also very sensitive to exact location. Even between Davis and Sacramento, you can have a quarter of an inch or half an inch difference for any given storm. So you can have quite a big difference depending on just where you make your measurement. So it's a lot of randomness there. But the bottom line is that the models don't do as well for precipitation. Forecasts of precipitation of the recent time period are not particularly skillful certainly compared to time. There's some general things which are probably correct. They're not particularly skillful. And any individual model is even less skillful. Turns out the average model turns out in almost any parameter, almost any variable, is better than any individual model, even the best model. Who knows? How about the future? This is an estimate from the CCSM for the temperature change in the year around the year 2050. This is a 10-year average in 95. And again, the temperature here, unfortunately, this projector and my screen don't look too much alike, but there's increases which are in the range of 2 or 3 degrees, pretty much like the global average. And here we see increases in the range of 4 or 5 degrees C, pretty much like the global average. So that the temperature change over California or over the western U.S. is pretty similar to what's observed in those lines which represented the northern hemisphere. And there's relatively small amount of variation. There's a tendency for the interior regions to warm up more, the oceanic regions to warm up less. Makes sense. The oceans have a large heat capacity. There's lots of reasons quickly, especially along the coast. This region along the coast, there's very little change, less than a degree in 2050. That helps San Francisco, and a relatively small change even in the 2055. We have quite a bit of confidence in these sorts of numbers, these sorts of evaluations, partly because of what I said about the forecast running to the present. When we look at the precipitation, this is for this one model, the precipitation estimate for 2050. So we have decrease in precipitation here and increase over here. This is the precipitation for 2095, where we have mostly weak decreases. Well, first off, I said we don't have a lot of confidence in the precipitation. And even worse here is that the same model gives us really quite a different pattern for 2 different time periods. And what's happening in those 2 time periods is the world as a whole is warming up. It just warmed up a lot more here in 2095 than there. And we saw in the temperature that basically, the 2050 was just a smaller version or the weaker version of the 2095. But in the precipitation, the 2050 and the 2095 don't have a lot of similarity in terms of pattern. So we don't really have much confidence in it. Nevertheless, there are some things that we can say. And this is from a work by Claudia Tibaldi. And she's done some things which kind of focus in on getting beyond just looking at the average temperature. So she's, for instance, looking at frost days. So this is the change for the period 2050, roughly. Change in the number of frost days over today. So we expect to have these 4 or 5 less frost days over this broad region than we have today. For growing season to be 3 or 4 degrees longer than today. For the number of heat waves to be, what are these numbers? Around 3 more heat waves than we have today. And warm nights to have 6 or 8 more warm nights than we have today. So all of these are in the same direction, but just helps us to identify something with parameters which maybe we can relate to or may be more important for instance, the warm nights for air conditioning. It has a large effect in the Central Valley because most of us can survive without running the air conditioning very much if it cools off at night. If it doesn't cool off at night, then the house gets pretty miserable pretty quickly for a couple-day period. So this kind of parameter may be more important than the average temperature. The other one that people have talked about is snowpack, and Phil showed something like this as well. What this is an estimate of the change in snow mass the year 2060 relative to 1995 over California. Unfortunately, the map of California is missing. The California coast is. All of these are the decreases. So all of these numbers are decreases. The decreases are least at the highest elevations. Not surprising. Very high mountains, the temperature is way below zero most of the winter, and the fact that it warms up, 0 centigrade, the fact that it warms up a little bit doesn't change the fact that you'll get snow. But on the peripheries, here where we have nearly 100% loss, if it warms up because we get rain and not snow, or we get very rapid melting. What this is a snow mass at the sort of end of the rainy year, snow season. So this is a measure of how much water is available for irrigation purposes, or the change in that amount of water. This prediction is based upon basically a temperature prediction only. This prediction assumes that the precipitation doesn't change. The total precipitation, total amount of rain and snow together doesn't change. All that's changing is basically we get more rain and less snow, or we get more melting in the warmer world. And this is the consequence. It's especially serious up here for around Lassen. Up here, the watershed feeding the Northern California, there's a very large decrease. Because these mountains are not as high as the southern. And so that the effect of warmer temperatures is greater. So that's about it. I just had a little inkling of California. I admit I sort of misrepresented my talk. But part of this was to give you a preview or a little basis for a number of the other talks, which we're going to talk about. For instance, next 2 weeks from now, is Jeff Mao is going to talk about water resources and things like that. To give you a way to think about how they're starting their talks. Now I'm not going to read this. I'm going to just take questions if anybody has any. Okay, the question is about the growth scenario assumed. Well, there are basically the two growth scenarios. The one which predicted the highest emissions also had the highest population growth. So there is a very strong link between the assumed population growth and the emission growth. Those predictions were the moderate predictions, yes. That's the A2, I think so. Anybody else? Clear as mud. So, okay. Well, the question is, why don't the models predict greater variability in the polar regions? Actually, they do predict a lot of variability, and that's one of the problems, is if you sample the future a given 5-year time period, you get a lot of change between one 5-year period and another 5-year period. So there is some statistical sampling issue. On the other hand, it is also true that for the recent time, no model has predicted the loss of Arctic ice as quickly as seems to be observed. So it's possible that we had some sort of a quirk in the last few years, but the models have not predicted that. So if anything, the models have been not sensitive enough. This is in the opposite sense of the naysayers and something, in terms of the effects of global warming. Okay, the assumptions about fuels are basically sort of blended into those sets of scenarios. In the A scenarios, there's an assumption that we'll go to more and more renewables and less fossil emitting fuels, carbon dioxide emitting. In the B scenarios, there's an assumption that it's basically business or some variation of that. So that's again why we have this range. One scenario gives us more or less rapid population growth and the current use of fossil fuels, not quite the current use, fuel regulation. The other scenario gives us relatively slow population growth, or slower population growth, and more renewables, non-fossil fuel, although certainly not to zero. So thank you very much.